Here we have a couple of situations, special cases to consider. If in the process of finding this quotient in here, the limit of this quotient, if we end up with a plus or minus infinity, what it indicates about the graph is that there's a vertical tangent at that point in question. So the graph, the point exists there, it's continuous, but the slope of the tangent becomes infinite, either positive or negative. Means we have a vertical tangent there. So it's one of these situations here graphically. That's what we're looking at. Okay, now the other one down here. Now we have the definition of the derivative of a function. I already talked about this in the last video example, but we have this here, the so-called derivative. It is defined like this, and we've already seen this. Notice the notation. We read this as f prime in here. See that? So we call it f prime typically. And we know that it stands for the first derivative. So that's not f to the first, that's a prime. So get used to seeing that, f prime. When this exists, it's called the derivative of f. And it is a function. We can use it just like we did in the last problem with it. When we computed f prime of c. Now there's some other notation things that we need to remember. We've got, for f prime of x, we have several. Here's one, we've seen that already. Here's another one, dy dx, we say that. We don't say dy over dx, we just say dy dx. Here, if your function is written as y, for instance, you might have like y equals x squared minus 2x plus 2. Then you would refer to y prime as the derivative. Okay, so you use that. You could use that prime notation in this case. Here's another one. This is called the differential notation. This one also is differential notation, but it's when we have a y instead of an f of x. This is when we have an f of x. It's still differential notation. And here, this is called operator notation. That might become useful when you work with calculus of several variables. This one becomes more useful, more practical for keeping track of things. That's the use of that. Let's see, where are we? I lost my page here. Here it is. Okay. So you'll typically see in this course, we tend to use this form, this one, this one, this one. You're not really going to see us use much of this one here. Not much use for it in this course. Now, let's go ahead and do another example here. We'll try to use some of our new notation. It says find f prime of x for the so-called derivative function for f of x equal x squared plus x. Then use that function to find the slope at the point 1, 2. Okay, so first things first, f prime of x will be equal to this limit, delta x heads to 0, for f of x plus delta x minus f of x over delta x. Now we have to do the algebra. Okay, so f of x plus delta x becomes an x plus delta x. You have to square that. Then you're going to add another x plus delta x, because that's what the formula calls for, right here. And then you're going to minus in plain old x squared plus x. And it's all divided by delta x. Let's continue. We got to expand this. We got an x squared plus 2x delta x plus a delta x squared plus an x plus a delta x minus x squared minus x. Okay, hopefully some of this will simplify, which it usually does. Oops. Okay, and now this becomes the limit as x approaches 0. I can get rid of a few things here. I can get rid of x squared, that minus x squared. What else? I got an x here and a minus x. And the rest of it looks like I'm kind of stuck with it. So I have 2x delta x plus delta x squared and then plus a delta x all divided by delta x. Okay, now notice also that as you come down this way, okay, the delta x's will cancel. This is something you have to look for. They'll divide out. Look for this in most of these problems. You have a 2x plus a delta x plus a 1, and that's all times the delta x over delta x. Okay, so I factor out delta x, and then that cancels, divides out, and now we're ready to find our limit. Notice at this point, if this is heading to 0, it looks like the only thing left is 2x plus a 1. So that's what we have. We have f prime of x equals 2x plus 1. Now you can evaluate it at, let's see, we want the point 1, 2. Okay, so at 1, 2, x is 1. So what we really need is f prime of 1, which is 2 times 1 plus 2, which is 3. That tells us the slope of the tangent to f of x at this point 1, 2. Okay, that's the point in question. 1, 2 is 3. And we could calculate actually quite easily the slope at any other point where this function exists, f prime. You just put in any number you want. It's a continuous function, 2x plus 1. That means that this curve has slope everywhere. Well, it's a continuous function, and not only is it continuous, our original function, but we recognize that as a pretty well-behaved function. X squared plus x is just a parabola. And it does have tangent lines to it everywhere. And it's never vertical, so we can expect our derivative to exist everywhere, since we're working with a continuous function that has non-vertical tangents everywhere. So our function can be used, f prime, to calculate any of those derivatives, to anything we want. We just found one right here. Almost seems like a waste to do all this work to find this function f prime and then just use one value of x to calculate a single slope. But that's all we needed for this problem. Okay, now here's another form of the derivative. I'm just going to go into this a little bit. When you're working with continuity and differentiability issues, a convenient form that you could use to calculate derivatives is this one. Okay, see, because what's good about this is that you can, this is our standard two-sided limit. And what that means is that we can approach this as two one-sided limits if we need to. So this is good for calculating slopes at endpoints on intervals, or at a break for a function. If there's a hole there or something, you want to investigate that. This is the form that you can use. Okay, so so in this form, if we, for instance, if we want to prove that a derivative doesn't exist at a point, this is a good form to do it with, because in order for this to exist, both of these must exist and be equal to each other. So using this form of the derivative is a good way to approach some sort of non-standard points where we suspect the derivative won't exist, but we don't have a way to prove it. We could do that with this form. Okay. Now we have also a few more ideas down in here I want to mention. Just make sure I didn't forget to mention them. Function is differentiable on the closed interval if it's differentiable on the open, and the derivative from the left at b and derivative from the right at a also exist. Okay, so if it's discontinuous at c, it will not be differentiable there. Okay, if it's discontinuous, it will not be differentiable. So that's important. Okay, if you have a discontinuity, you will not have a derivative there. Okay, so that's the issue. And here's our main theorem here. If it's differentiable, it must be continuous. That's what this says. We know the converse of that is not true. If it's continuous, it doesn't have to be differentiable. But if it's differentiable, then it must be continuous. Okay, let's do one more example here. Actually, it's a couple examples. But, all right, let's just do one example and then we'll go to another video. So for this one, determine if this function is differentiable at x equals 0. So here's what we do. Okay, I did a little bit of the work here, just to speed things up. Not necessary for everybody to see all of this. So let's start off with this is our two-sided. So this is one option. If you can find, this would be f prime of x. If you can find it, and that might be a challenge algebraically, then you can evaluate it when x is 0, if possible, and that would determine your answer to the question, whether or not it's differentiable. Now, the alternate, now this, how can you expand this? This is 1/5 power. Without using the binomial theorem, it would be kind of difficult, and nobody has the binomial theorem, and just handy, so to speak. So this could be done, but it would be a lot of work. But you could do it. You could get this done. Now, a simpler way would just be to take the approach using two of these. We've got the derivative from the right at 0 and the derivative from the left at 0. If you can find that both of these are the same, if they both exist and are equal, then you have a derivative and it's differentiable. Now, doing one of these, you immediately find, when you put in your numbers, that you get an infinite derivative, or you could say undefined, but it's definitely infinite. So that would be enough to just say, okay, stop, I'm done. This is not differentiable. You'd be finished. But if you really want to satisfy your curiosity, you could continue and find the derivative from the left and notice that it's also infinite. So we found a point where the derivative does not exist, and that's here at x equals 0. It is not differentiable there because of that, because you have infinite derivatives. When that happens, you consider the derivative to be non-existent at that point. Okay, now graphically, it means we basically have vertical asymptote there, which is useful. But in terms of the derivative, we don't have a function value there, derivative function value. Okay, so that. Okay, now example 5 says show why this does not have a derivative at x equals 3. Well, again, you start with your two-sided derivative. In other words, the limit as x approaches 3 with f of x minus f of 3 over x minus 3. Now, the trouble with that is that it contains the absolute value function here. when you put that in, and it's going to be hard to work with that, but we could try it. Let's see what happens here. Going to 3, we have x minus 3 like that, and we have f of 3 is a 0, so we'll have that, and then down here we have x minus 3. So that's this. Okay, now, so the problem here is that you may realize right away that you're going to have two answers for this limit, not a single answer. And the reason is because notice that this absolute value, essentially it means that the x minus 3 can be positive or it can be negative. It doesn't really matter. That's what this says up here, that it will be the same when you put absolute value bars on it. But the denominator will not be the same if it's negative. So in other words, the numerator may always be positive, and then the denominator changes its sign depending on the direction of the size of x. So this is saying that x is approaching 3, but depending on the direction that you approach 3, either from the left or the right, the denominator might be positive or negative. In either case, what you're going to see is a plus or minus 1. Now, that might be hard to see that. So let's look at a two-sided limit. In other words, break this down into two one-sided limits. It is a two-sided limit right now. Let's break it down to this. X goes to 3 from the left. We have f of x minus f of 3 over x minus 3. So that's the limit. So this is more fine detail about what I was saying over here with regard to the signs of these expressions. So x is going to 3 from the left. Our numerator, you have to think about this function here. It's x minus 3 like that, minus f of 3, which is a 0. Okay, and then you have x minus 3 down here.